be making a start in just a moment. If you've got any questions as we're going through, please feel free to ask your questions using the questions functionality in GoToWebinar. It's fantastic to see so many of you here. So let's make a start. Next slide, please, Anirudh. Thank you. So first of all, I'll introduce myself. Hi, I'm Steve Lenne. I'm an application engineering manager at SimScale, and I'm going to be your host today. I'm joined by Anirudh, and he's going to be the star of the show today, doing the actual demonstration. Anirudh has got a background in CFD for mechanical design in the automotive and aerospace industry, and a master's in mechanical engineering from Carnegie Mellon University. Anirudh is a valuable asset to our application engineering team here at SimScale. So let's go on to the introduction now. First of all, I'm going to give you an introduction to SimScale, and then Anirudh will go through the demonstration. So who are we? Well, we're a Munich-based company. We were founded in 2012, and we've got millions of simulation jobs being conducted worldwide at the moment. And we're funded, so we're going to be here to stay. What do we do here at SimScale? Well, we created the world's first cloud-based engineering simulation platform. And this platform allows you to do fluid dynamics, CFD, solid mechanics, FEA, and thermodynamic analysis. The fantastic thing about SimScale is all of this is available through your web browser. There's thousands of companies worldwide that trust SimScale for their simulations. Here on the screen, you can see a few of those brands that work with us and trust us. How do they use SimScale? Well, they use SimScale to accelerate their design process, to simulate earlier in the design process, to test performance, optimize durability, and improve their design efficiency with our cloud-based simulation platform. How does this compare to traditional CAE? Well, with traditional CAE, you typically have high fixed costs. It relies on specialist hardware that you have to install and maintain, and specialist software that you have to install and maintain on that hardware. Typically, this software is built to be used by specialists. So that means that there's extensive training and experience required to get the most out of the software. The computing time is typically measured in days or weeks, and it's difficult to parallelize simulations because your hardware and software is occupied during a simulation. So how does this compare to what we offer with SimScale? What are the benefits of SimScale? Well, there's no upfront investment required. You don't have to purchase or maintain any expensive hardware. And there's no installation or maintenance of software either. It's incredibly easy to set up. All you need to do to set up an account is go to our website, create an account, and start simulating. We allow you to have seamless collaboration between your departments so you can share projects and work together. And at SimScale, we provide world-class support embedded within the software. You can use the chat functionality to reach out to our team of simulation experts for advice or help on your simulations. Computing time is typically measured in minutes rather than weeks. And you can leverage the capabilities of cloud simulation by running as many parallel processes as you like. So that's enough of an introduction from me. I'm going to hand over to Anirudh now.
Thanks, Steve. So today I'm really excited to showcase some of SimScale's features and how you can implement it into your workflow, specifically to model any type of rotating machinery. So the example I have for you today is of a Francis turbine, but all of the principles, all of the simulation setup that I show you today can be applied to any kind of rotating machinery, really. So this includes things like pumps, fans, blowers, compressors, propellers, any kind of turbine, anything really with a rotational component on it. You can use the same CFD or modeling strategies that I show you. The reason I chose Francis turbines is because they're a good combination of axial and radial flow, and they're used widely in the hydropower industry, accounting for more than 60% of the global power output. So that means any changes or any improvements that we can make in the efficiency will have a significant effect down the line. So the objective today is to look at the design of a Francis turbine, characterize its performance, and see how we can optimize or improve its design. So this is a quick overview of the geometry that I'm using today. So it's a pretty standard Francis turbine. It has an inlet. Here, as you can see, the water moves around through the spiral casing, and that gets redirected onto these guide vanes or these fixed plates that you can see. So they direct the flow towards the moving blades or runners, and this is the part that actually rotates and generates the power. So you can think of the fixed plates as stators and the moving blades as a rotor. Once the water goes through the rotors, it comes down through this draft tube where it is sort of equalized and exits to the environment or exits outside. And the job of the draft tube is to minimize any losses in that process. So quick overview of how we'll set up this simulation. We have a simple CAD body, like I mentioned. We have a second CAD body around the MRF, around the rotating zone to capture the blades. So it is a pretty straightforward simulation condition where I'm specifying the material properties as well as the inlet. So I'm specifying a flow rate, and at the outlet is just a static pressure. And also in this cylindrical area in the blades, I'm specifying the rotation. So it's simple, incompressible, steady state flow. And this is just a quick note on the setup. So let's exit the presentation and look at this in the platform. Right. So this is the SimScale platform, and right up top, the first thing I want to point out is the URL. So you can see that this is completely browser-based. I just have a simple Google Chrome tab open. I don't have any fancy hardware installed. It's just running on a simple Lenovo ThinkPad, which is my work laptop. So the plan is to first look at some of the results that you can get from running a simulation like this, and then I'm going to show you how easy it is to set up. So right now, like I mentioned, I already ran the simulation using the setup conditions that I had shown you earlier, and we're taking a look at some of the results. So the first thing I would want to do is to analyze just the general flow behavior in my domain, and I can do that using these what we call particle traces. So you're just following a fluid as it moves through the domain, and I'm kind of interested in looking at the large-scale flow features in my domain. So I can kind of see how the fluid moves around from the inlet, rotates through to the guide vanes, then through the moving blades, comes down, and you can kind of see this swirl or rotational component that is imparted to the fluid by these turbine blades. So I can kind of follow that and see how that exits out of my domain. So this is a great way to get a good qualitative understanding of the larger flow features, any kind of recirculation or any kind of rotation in your domain. So let me pause this animation and let's take a look at some more bulk results. So now I want to understand, for a turbine like this, it's crucial to understand the flow rate and the pressure head or the pressure differential that's in my domain. So instead of coloring the part a color, I can just color it by a different result. So instead of this, I can say, okay, I want to look at the pressure, and my entire domain is highlighted by pressure. Now, in order to get the pressure head, what I can very easily do is just click on a surface like the inlet and toggle on this bulk calculator. So this gives me the average pressure. So it is about 273 psi, which is the differential across my system or the pressure head. I can use a different unit if I'm familiar with, say, megapascals, and it'll update the units and give me that value. Similarly, now that I have the pressure differential across my system, I want to know what kind of flow rate this is pulling. So instead of pressure, I can very easily just change this result to velocity. And when I do that, you'll notice that it gives me the average velocity as well as the volumetric flow rate at the bottom. So now that I've kind of understood these characteristics about my turbine, I want to dig in a little bit deeper and understand more specifically what's going on around my blades. So I can do that by using a cutting plane, which I have already created. So what this does is slice the domain right through the middle, and now it lets me investigate what's going on around the blades. So if I zoom in, I can kind of see that, especially around the stators, which are my fixed blades, I can see a significant amount of flow separation, sorry, and recirculation. The blades on the left here look slightly better where the flow is attached, but the blades in most of the domain don't look pretty good. I can use these arrows to kind of understand the direction of the flow and the length to understand the magnitude of the velocity. So now that I've understood how the flow is around my blades, I want to see how my draft tube is performing. So I can do that very easily by changing the position of this cut plane. So let me turn off these vectors, and instead of looking at it through the Y normal, so I can look at my V cube at the bottom right and make sure it's oriented according to the X normal. So what that does is slice the domain in a different way, and now I can see what's happening in my domain through the draft tube. So with the draft tube, like I had mentioned, the job is to try and minimize any losses and equalize the pressure. So again, instead of looking at the velocity, I would just click pressure, and this sort of gives me an idea of what the pressure differential is across my system. So I can straight away see by looking at the legend here that I see a pretty steep transition. So green is higher pressure and yellow is lower pressure. I really want this to be as smooth as possible. So right now, there is a lot of potential for improvement and optimization of this design. So this is just a quick example of some of the features of SimScale that you can use, some of the post-processing features that you can use to gain insight into your design, and this can inform any of your design decisions or help you characterize the performance. So I can very easily just use this inspect tool and look at my pressure just to see how it is changing across the domain. So I can probe individual points, and that kind of tells me how the pressure is changing. Right, so now I'm going to show you how I set up this simulation. So let me go to the Geometries tab and give you a quick overview of the UI. So you can see here on the top left, I have a few geometries or CAD models imported. On the bottom, I have the simulations, and this is where I control all my simulation parameters. In the middle is the 3D view, as you have probably guessed by now, and on the right, I have a breakup of my geometry. Up top, I also have some sharing and collaboration features, so I can copy my project very easily, or I can share it as well. I can give edit rights to certain people and almost use like a Google Docs approach to collaboration, where I can have different level of rights to different users. So let's get started with the setup, and we'll get started with the CAD. So you can upload any amount of any number of designs as you want. I already have 4. I can just click on this import button and upload any of my CAD models. As you can see, we work with most CAD formats. The only thing I need here is the fluid domain of my turbine, and I have a second body, as you can see, which is just a cylindrical body around my blades, and that helps me model the rotation. So let's get started with the simulation. I can hit create simulation, and this opens up the full suite of physics that SimScale can handle. So you can see it's not just CFD or flow simulations. If I have some heat transfer, I can take that into account as well. I can also do structural simulations. So I can say do an FEA or finite element analysis on my blades and see how the pressure forces cause any sort of deformation. So I'm going to, in this case, I'm just going to create a quick incompressible simulation. And you'll notice when I do that, I get a new simulation here called incompressible 3. So I can rename this to whatever I want. I can just call this Thursday demo for now, and I can get started. You'll see that there's a few tabs under, or a few branches you can say under my simulation tree, and the setup process is pretty straightforward. So I need to get a green checkbox everywhere, and if I have a red circle, that means something's wrong and the software won't let me run a simulation. So as you can see, I have a couple of red dots here. So there's only a couple of things I need to change. One is to define the materials. So I can hit the plus here, and this opens up our material library. I'll just choose water for this case. The only thing to note here is that I can vary any of these properties to suit the material in my domain. So instead of water, if I had a different mixture or a different liquid, I can very easily just edit any of these properties, as you can see, and even rename my material. So the next thing I need to address is the boundary condition. So this is where I'm specifying my inlets and outlets. So in my case, like I mentioned earlier, I want to specify the flow rate through my domain, and I can do that using a velocity inlet. So what that lets me do is I can select my inlet, and instead of specifying individual velocity components, I would prefer to specify a flow rate, and I can do that very easily. Change this to volumetric flow and say 16 meter cube per second. I can again use a different unit if I'm interested, or if I'm more comfortable with that unit. At the outlet, it's pretty straightforward. It's just zero static pressure because it's sort of exiting out of the turbine, and I can just select that and assign zero pressure. The only additional thing I need to do here now is specify the rotation, and that is hidden here under advanced concepts. So we have something called rotating zones, and I would use an MRF zone or multiple reference frames. So what this means is you have two reference frames. You have your normal domain, and you have this cylindrical body, which would be your second reference frame. So this is what I had created along with my CAD. And here what I'm specifying is just the axis of rotation as well as the origin of that second reference frame. So what this intelligently does is, since you're specifying the rotation as well as the origin, so let me just quickly specify the rotation here. This is about 350 RPM. So using the two inputs of this domain, we can very intelligently run a steady state analysis, and we don't have to say use like a moving mesh or a transient analysis. We can use the information from these two reference frames and overlay to get a good steady state solution. So now you can see I have green check boxes everywhere, and I am good to go. So I can hit simulation run here to set off a new simulation based on these conditions that I had specified. So I get a quick estimate of how much time and how many computational resources this is going to take. And if I hit start, you'll see that the simulation job is sent off to the cloud. So I don't have to worry about this. I'll get an email when it's complete, and I can come back and look at the results. So if I want to say study a different operating point, maybe get out a bump curve or something like that, I can very easily do that and change any of my input parameters. So let me go back to my velocity inlet where I'd specified the flow rate. Instead of 16, I want to study a different operating point, and I can hit 12 here and hit OK. After that, I can just hit the plus button here and start a new simulation run. So I can call this, I can rename this to 12 meter cube per second and hit OK. And you'll notice that even this run is set off to a different virtual machine in the cloud. So what this means is you can really harness SimScale's cloud capabilities and parallel computational capabilities to run as many simulations as you want. So I can do like a full-blown design study, and I'll show you some of the results for that later. The last thing I want to show you is how you can look at different designs. So I have a couple of different designs here, and I will go back to the presentation and compare some results. So I have a second design here, which has a slightly different draft tube outlet. So it has a square cross section, and it has different stator blade angles, since we observed some amount of flow separation with the previous design. Instead of having to set this new design up from scratch, what I can do is I can just duplicate my existing simulation. So if I hit duplicate, that creates a copy of my first simulation, and I can very easily just switch out the geometry and run my second design that way. Now, as I've shown you, this is the process is pretty straightforward, but if you do run into any trouble, we have in-product chat as our main form of support on the platform. So on the bottom right here, you can click this chat icon and send us a message. So this is staffed full-time by our support engineers who will get back to you within a few minutes. So this really, so what this does is you have this share project with support checkbox. So by default, all your projects are completely private. Even we don't have access to it, nor do the cloud servers. But if you enable this checkbox, then our support staff get view-only access to your project. So using the same URL, they can pull up your project, and they will be looking at exactly what you're looking at in real time. So that makes the support instantaneous. Unlike traditional on-premise software, you don't have to file a support ticket and send over a bunch of data and wait for people to respond. It's really instantaneous and pretty revolutionary, I'd say. So now that I've shown you how you can run a design study and compare different operating points on SimScale, I want to quickly take you through some of the result comparisons in the slide again. So let's come back to this and look at the comparisons of the two different designs we have. So let's look at the cut plane through the through the runner blades, through the guide vanes and the runner blades. So on the left is the first design that I had showed you on the platform, the second on the right is the second design with a slightly different stator or guide vane angle. So what you can clearly see here is if I zoom in, you can see that after we have changed the angle of the stator blades, you will see that there is far less flow separation. So this is a good way to compare different stator blade designs, stator blade angles, and see what really works best, what has the least amount of flow separation and does a good job of redirecting all your flow onto the moving or the runner blades. Let's quickly look at the two different draft tube designs as well. On the right was the square draft tube. And if you remember, I'd said the job of the draft tube is to really equalize the pressure to minimize any losses. So you don't want to see any of those sudden pressure drops that I had pointed out on the platform. So on the left is the design I showed you, where you can see the pressure drop from green to yellow, so high to low, low to high. It's pretty steep. The gradient is pretty steep. Whereas on the right with the newer design and the circular draft tube, I can see that the pressure gradient is much smoother and therefore the losses will be much lesser. Let's look at the flow coming out of the exit as well. So these are the particle traces or the streamlines that I had seen earlier for the velocities. And again, I can see that with the circular draft tube, I see a lot of the swirl component and rotation at the outlet, whereas with the square design on the right, it's a lot lesser, and therefore the losses or the energy losses are going to be a lot lesser. The last thing I want to quickly show is looking at the pressures on the blade surface. So this is what we use to calculate the torque. So once we have the torque, given the pressure differential on the blade surfaces, we can multiply it with the RPM to get the power, and that is how we would calculate the efficiency. Right. And so when I showed you the different operating conditions that we could simulate on the platform, I use that to create some performance curves for this turbine. So on the left, I have efficiency versus flow rate. So I'd studied different flow rates for these two designs, and I can sort of see which is my most optimum point or my best efficiency point. On the right is the different stator angles. So I've compared the angle at the bottom and plotted the efficiency. And this is what I've used to determine what angle of my blades works best to give me the most amount of efficiency. So I've covered a lot of information pretty quickly, and I know that I've gone through a lot of these results. So if you have any questions, again, I would highly encourage you to write them in the chat and we can address them now.
That's fantastic. Thanks for that, Anirudh. And yeah, please ask any questions that you've got. We've got a couple come in here that we can go through in the next 5 minutes. So the first question that we've got is, are simulation jobs throttled or queued in the cloud? I guess this is around when you set off the multiple simulations.
Yep. That's a good question. So the short answer is no, we absolutely do not restrict you. The simulations are not queued and they are in fact running in parallel. So if I go back to my simulation here, you can see that I have those two simulations and they're already running together in parallel. They're both running on virtual machines in the cloud, and under simulation control, I have the ability to choose which machine I want to run them on. So right now it's set to automatic. It'll choose the most efficient machine, but I can choose up to a 96 core machine to run this on. So you have access to theoretically an infinite number of these machines, and you can run all your simulations in parallel on them. There's absolutely no restriction other than the core hour usage or how many computational hours you end up using.
Great, thanks. What would be the reason for choosing a machine with lower cores there, Anirudh? Why wouldn't you just select 96 every time?
Sure, yeah, that's again a common thought, I'd say. So there's certain rules of parallelization where it doesn't make sense to just run every simulation job on the biggest, baddest machine that you can find. Because when you want to split a simulation job into 96 individual cores, there's a lot of processing that goes into splitting these jobs, sending them off to the cores, getting them back and combining them again. So a lot of times it's more efficient, especially if you have smaller meshes, to choose a lower machine. So we do that automatically to choose the most efficient machine. But if you are in a hurry or if you want to design results much faster, we give you the option to manually choose a bigger machine and get quick results.
Great, thanks. Okay, so another question that we've had come in is, can I get the flow rate and forces from the simulation outputs without using the post-processing analysis?
Yep. Yep. There's a way to definitely do that. So a lot of times we see that when customers want to run these sort of design studies with multiple operating points, they're just interested in looking at the macro numbers like the flow rate, forces, pressure head. You don't need to go into the post processor and extract those manually each time. There is a way to set it up beforehand under result control. So this is hidden here, and you have the ability to set up reports for forces and moments for surfaces. So to get the flow rate and say the pressure drop, I would set up an area average for this inlet and outlet like I have done here. And once, if you set this up in advance, what this helps you do is on the results, I don't have to open up the post processor. I can directly access this forces plot and this to get the torque, which I can use to calculate my power. So as you can see, this gives me a breakdown based on the XYZ as well as the different forces. So my torque would be the pressure moment about Y. So if I click that, you can see that the graph is highlighted. I can export this as a CSV as well. Same thing with the area averages. Again, I can just click on these to get the numerical data.
Great, thanks for that. Okay, if there's any more questions, please feel free to submit those. Otherwise, we'll close in just under a minute. Okay, if there's no other questions, I'll thank everyone for attending. Thank you very much, and we'll see you soon.
Thank you.
Bye.